Here I have two very similar frequency doublers. They are designed to double the frequency from 10 MHz to 20 MHz at a power level of half a watt input. Here is the schematic diagram. It's fairly similar to what I've shown in the previous video, but I added 3 more turns on the primary winding here to get a better impedance matching. And then another fairly important thing is this series resonator between the two sources. It's tuned to the third overtone, 30 MHz, and it improves the output level significantly. And this resistor is now 33 ohms. It was 47 before, but this seems to be kind of an optimum. I had to add this RC link, 12 ohms, 12 PF, to prevent oscillations at VHF or UHF frequencies. I have a plus 27 dBm 10 MHz signal coming this way and going out here and into the spectrum analyzer up there. And then there are two outputs at minus 20 dB, one forward and one for the reverse wave. And you can see the signals here. Forward is the lower track and reverse is the upper one. And it should be visible here that the power is 26.9 dBm. I am now sending that signal into one of the frequency doublers and looking at the output with the spectrum analyzer. And you can see here there is some leakage of 10 MHz, not very strong. But the 20 MHz signal is 29.3. It means I have a 2.3 dB gain in the conversion from 10 to 20 MHz. And you can see the reverse power is something like 10%, means about 20 dB return loss. So it's pretty well matched to 50 ohms. And I go for the other here, so I just change like that. And you can see this impedance is very similar. And the level is 29.5. So these two amplifiers are very similar in conversion gain and impedance. Here is the noise I see after applying a selective load and the notch filter. And you can see the noise is minus 191.3 dBc per hertz. I've calibrated things the usual way, and I just go for the other one. And now the amplitude has changed by a couple of tenths of a dB, but the noise is very similar as I had before. It's now minus 191.6. So I don't care about the decibels now, the decimals now. What I want to do is to use these two in an interferometric setup to look at the close range noise. This is the interferometric setup for studying the two frequency doublers. It starts with a 10 MHz oscillator. It gives 30.0 dBm. a stepped attenuator which is now set to 0, and it's plus 30 on the other side of it. Then there is a 90-degree hybrid splitter for 10 megahertz, and it splits the signal in two equal parts, 26.8 dBm here and 26.9 dBm here. The two legs of the interferometer are in red. So this way goes through a phase adjustment. It's cables that can be switched and a continuous phase tuner. And that reduces the power by 0.2 dB. Then there is the frequency doubler, and the output of that is 29.4 dBm. And then there is a continuous amplitude adjustment, and then it goes into a second hybrid. This one is for 20 megahertz. The other leg, it comes here, goes through the doubler, and the output here is 28.9. So it is half a dB lower than what I see here. The multipliers are a little different. Then there is a 20 dB coupler where I can insert a signal from a signal generator through a 20 dB attenuator in here and to a dummy load. And then there is a second coupler by which I can measure what passes through in this leg. And that signal goes, the measurement signal I can take out, attenuate by 10 dB, band pass at 20 megahertz, and then 20 dB attenuation, and then there is the Perseus. Here I can look at the amplitude relation between the signal, the frequency doubled signal, and the signal I am injecting from the signal generator. And then I have another 10 dB attenuator and a net aphedry, where I can look at the same thing, but at another amplitude scale if I want to. The signal in this leg here goes then to the hybrid, where it is combined. The hybrid generates a sum signal. It is plus 31.6 dBm here. I have a 3 dB attenuator to protect this stepped attenuator, which is needed to not saturate the oscilloscope. And this channel, I use it for triggering the oscilloscope. That makes it easier to see while doing the balancing. The difference output, that's the interesting output. It goes to an impedance match to make this stepped attenuator look into a 50 ohm source. Then there is a 20 megahertz bandpass filter, followed by a low noise amplifier with JFET transistors. Then there is an impedance match. So I forgot I have changed this. After the LNA is another low noise amplifier, an AMC 147. Both these amplifiers have noiseless feedback, which means that the output impedance is mirrored on the input. So I can move the impedance match all the way here and still tune this to get the impedance seen by the stepped attenuator precisely 50 ohms. So I know that it's 50 ohms on both sides of this. So I can measure the noise figure here in a 50 ohm system And I also know that if I change the value on the attenuator, I can read on the stepped attenuator how much attenuation I actually had. But more important, when I apply attenuation here, I will know that the noise figure will not change. And more important, the gain through here will not change. So I can see the noise floor of the receive system and separate it from the noise that comes from the interferometer. Because the noise from the interferometer is not very high above the noise floor. And then after the impedance match there is an attenuator and a PSA4 5047. It has very high gain. So I remove a lot of the gain that it provides by having this 10 dB and another 3 dB at the output. Then there is an 8 dB coupler where I can pick up a little of the signal and put on the oscilloscope where I look when doing the tuning. And then there is the receiver where I study the noise. It's the SDR IP. First I will look at the impedance here and demonstrate what it looks like. It's necessary to run the network analyzer at a very low power. I can change it, let's say 50. Sorry, minus 50. And it doesn't change much. I can read 51 ohms or 50.5. I can go to minus 40. Minus 30. Now it has increased a little, I think. Minus 20. Now something is heavily saturated. Anyway, the impedance is very close to 50 ohms at the output of the attenuator, means the input of the receive system for noise. And here's the output impedance of the stepped attenuator when it is set to 0 attenuation. It means it's the impedance feeding the low noise amplifier. And I can make the scale different, 0.1. And you can see that the various jumps around, because there is some 20 megahertz around, but here is the impedance I have. It's maybe 2 ohms away from the perfect value. I will also look for the noise figure at the input of this bandpass filter. And I have set this noise source to 4 dB. It's in the low range. And then I look for the noise floor, which is 3.1. And then I switch off this noise source. And I did calibrate recently, so I expect to see 0 now. So actually it said 4.1 because it's not very stable, that noise source. So the noise figure is 4 dB. So the noise floor here should be minus 170 dBm per hertz. And if I neglect losses here and here, I expect close to minus 170 at this point dBm per hertz. The signal is about 28 dBm, 28.6 at this point. And there are 2 such signals, and they cancel. But I want to refer the noise to the level of one of the signals. That's how I'm going to calibrate. So one signal plus 28 means that the limit for what I can see is something like minus 198 dBc per hertz. At that point, the receiver noise from this LNA is going to be 50% of the noise. We will see what happens when I do this in the real world. The frequency response of the Perseus is not perfectly flat. I can expand the scale and you can see easier here. The ripple is about plus minus half a dB. So I will insert a signal from a pulse generator to calibrate for a flat frequency response. To calibrate the Perseus, I have a pulse generator, run it through the bandpass filter, and the output from the bandpass filter goes directly to the Perseus. So this bandpass filter is seeing 50 ohms here due to this attenuator or from the Perseus. The output impedance of the pulsar is 50 ohms, of course. To calibrate the amplitude response for the SDR-IP, including everything that is in front of it, impedance match and amplifiers and this bandpass filter, I have disconnected the output from the doublers here and here. And then I have inserted the pulse generator, the pulsar, into this coupler here. And here's the frequency response I see. This is with the pulsar running. Now the response of the SDR-IP, including filters in front of it, is very flat. I can expand the dB scale to show that better. And you can see there is some little error here at the center. So I move the frequency to not have 20 megahertz very close to the center. So I change the frequency to 20.1. And of course, then nothing is okay anymore because the dominating effect on the frequency response is the filter. So I have to recalibrate. Now the response is flat and the center problem is here and it's much smaller. The reason it was so big before was that I had some leakage of 20 megahertz into this. But now I switched off the oscillator, so this interference is no longer present. I have set the Linrad S meter to show 0 for the carrier at 20 megahertz. And now I inject a signal 400 kilohertz below. And it comes here. And I have set that to be 80 decibels below the carrier, 80.02. So this is my reference signal. And then I look in the SDR-IP. I want this reference to be at minus 80, which is indeed is. And then I switch off that signal. And here comes the noise floor. And I have added a function to get it in decibel per hertz. so I don't have to set any particular bandwidth anymore. So reading it out here, I find minus 189.7 dBc per hertz. I now add 20 dB of attenuation in front of the low noise amplifier. Like that. And here is the noise of the receive system. And it's not much lower than the sideband noise I observed. So it comes at minus 193.5. So I will make a table with measured data at different frequencies. And since I saw here the difference is only 3 dB when inserting a lot of attenuation, it means that the sideband noise is in the order of minus 192 or 192.5. I will compute that properly and add a column for that. And that is the summed noise of two frequency doublers, which means that one frequency doubler should be at about minus 195. And that is AM noise plus phase noise. Now I am at 1 kilohertz separation, and in the passives I have minus 80 decibels. And I look at the carrier here, and it doesn't need any good statistics. It shows 0.02. So the injected signal has the appropriate signal level. And then I look in the SDR IP on the signal 1 kilohertz below the carrier, and it indicates 80.0. And then I switch off that signal, and here is the noise floor. And you can see when I'm talking too loud, there is microphonic on my system, so I have to keep quiet. And now I waited long enough, I think. No. Here, 185.3 minus 185.3. And the amplifier noise is minus 194.95. Well, that's minus 195. Similar to what I have seen before. Minus 195. So it's clear I'm now reaching the flicker noise region, because the noise is going up. So it is now 10 dB above the system noise. And that is 1 kilohertz. Now the pilot tone is 310 hertz below the carrier. And I have set the S meter to show minus 80, which is the level I also see in lean rod. And I didn't change anything because the frequency changes are small now. And I switch off the signal generator, and I have to wait for a long time now. The noise is minus 180.8 dBc per hertz. And actually it is a little bit lower because I have a spur here. The amplifier noise at 310 Hertz offset is of course the same as at other close offsets. It is minus 195 dBc per hertz. And the sideband noise is 15 decibels higher, so the amplifier noise does not affect the result at this close separation. This is 70 Hertz below the carrier, and the level I see is minus 173.4 dBc per Hertz. This is 10 Hertz separation, and the level I see is minus 160.9. Here is a separation of 2 Hertz, and it has changed with time, but I take this part here and can see minus 148.5. It takes a long time, but here's the result at the separation of 1 Hertz. What? I have to repeat it. This is now a separation of 1 Hertz, and the level I see here is minus 143.6 dBc per Hertz. But maybe the bandwidth is a little bit too large. You can see how the slope of the noise changes over the bandwidth. This is a separation of 1 Hertz at a slightly narrower bandwidth. And what I see here is minus 140.8 dBc per Hertz. Here is what I found. There is the measured noise, sideband noise plus amplifier noise. And here is the amplifier noise. So I convert from dB to linear power for this and that and subtract them, and this is the noise, the sideband noise, and log frequency. And I plot these numbers on the same graph where I have plotted the performance of Schottky diode frequency doublers. And of course the power is much higher. The output is plus 29 dBm for this active device, but for the Schottky diode doublers the highest power is plus 15 dBm, but then the noise is fairly high. Reducing the signal level reduces the flicker noise. So at plus 21 dBm input and 11 dBm output, I have this lower curve here. But it flattens out at a fairly high level, something like minus 177 dBc per Hertz. Now this active doubler has much higher output, and it has some, I don't know if this is real or something with the filters and the calibration procedure I have used, but it's in the order of minus 190, maybe minus 192 or so. And it stays low up to about a separation of 1 kilohertz. And then it goes up, and it goes up much steeper than expected. So this is not flicker noise, and I don't like it. Here is the setup. Some units run on 15 volts and some run on 25 volts. I have added the big capacitors that I have on the supply voltages, and I have also added resistors from the power supply. Here is 4.5 ohm, and these two together are 0.1 farad. And this one is 60,000, and I don't know what that one is, but probably around 0.1 farad. But there's less current here, because here is the 15 volt supply. So here the resistor is 15 ohms, while this resistor is only 4.7 ohms. But noise at frequencies down to 1 hertz should have been reduced significantly by this. I see no difference at 10 hertz and above, but here is a separation of 2 hertz, and what I see now is minus 153.4. Well, once more. It's slow with these bandwidths. Minus 153.4. Now, that is significantly better than the minus 148 I have seen before. But at 10 Hz I still see 160.9. Here I am at a separation of 1 Hz. And as you can see in the S-meter graph, things are not stable. At the moment I have been at minus 147. It was minus 143 before. But when I started it was at minus 150.5. And the problem is the balancing of the interferometer. The upper track shows the balance, and you can see vibrations. I closed the drawer on the workbench. Well, I tried to reduce here. It is non-trivial because of mechanical issues. Well, something like this. But it will not last very long. I am doing this study in the middle of the night. It's now midnight. To avoid the temperature changes due to the different effects of the sunshine. And I will have to wait a little, and hopefully the balance stays good for a while. I run the S-meter graph a bit faster, so I am trying to catch the moments where the interferometer balancing is good, like here. Minus 150.4 dBc per hertz. With better supply voltage filtering, I get a better straight line from here, 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 and here. But the slope is steeper than 1 over f. And I cannot explain that, so it's not flicker noise. Maybe there is some problem due to 7812 voltage regulators that I have inside various boxes. They can have flicker noise that modulates things. But anyway, the performance of the frequency doublers at close range. If it is 135 or if it's minus 150, doesn't really matter so much, because when we look at the oscillators, my best oscillator is something like maybe minus 80 or minus 70 at 1 Hertz. And that's the same for the phase noise of the citrine that Wenzel produces, but that is at 100 megahertz. So at 10 megahertz it should be 20 dB better, but still that is far above the noise from frequency doublers. So they are all good enough here, but the JFET doubler is very much better at wide separations. Please note that what I am measuring here on oscillators and doublers is under idealized circumstances, because I do not worry about the spurs that come from mechanical vibration and also magnetic fields due to the connectors I'm using that have nickel on under the gold. In real world applications, one has to isolate from magnetic fields and from one has to isolate from mechanical vibrations. That is fundamental. But probably also from magnetic fields, because there could be components that have some ferromagnetic properties involved in the oscillators. So the whole business of making very good oscillators is far more complicated than what I am demonstrating in this series for nerds. It's just one side of it, and my main focus is sideband noise at wide separations. That comes from my interest in running full duplex on VHF transmitting with a kilowatt amplifier, and at the same time listen at a close range what the other people are doing on the band. I have been doing that in the past, and with the accumulating knowledge I'm getting now, I could do it better. But I'm too old now to be on the air, I think. But I find these experiments rather interesting.